Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
In this example, we have this circuit here with a single resistor and a metal bar sliding across the wires of our circuit. And we are creating an induced EMF in our circuit by moving this metal bar here through a magnetic field. And so we're sliding it along with our hand with a certain amount of force, F here, and we're keeping it moving at a constant velocity. And because we're doing this, given all these parameters here, like the magnetic field length and velocity, we managed to produce a current of 0.4 amps in our circuit. And what we want to know is what is the average power that we are delivering to the circuit by keeping this bar moving along like this. So normally, if imagine we weren't pushing the bar here along the circuit, we just let it go with an initial velocity v, what would happen is that the bar would eventually slow down to a stop because all of this energy from the original motion of the bar is going to end up getting converted into energy that's used by the circuit. So since we're holding the bar and keeping it moving along, we're preventing it from slowing down. So we're actually putting work in to this system. So the thing to realize here is that the energy that's being used up by the circuit, so the power rate of dissipation of energy by the circuit, which I'll call P sub C, is going to be equal to the work that we're putting in, the rate of the work we're putting in with our hand, to the power from our hand. So those two things are going to be equal. So if we can just find how much energy is being dissipated in the circuit, then we'll know exactly how much we're delivering by hand here. So we should recall that the power dissipation in our resistor here is going to be equal to V squared over the resistance of that resistor, or in this case, our voltage is just going to be our induced EMF. So we'll have our induced EMF squared over R. Or if you don't know the resistance, we can substitute out for Ohm's law here for one of our for an E over R, and just have the current times the induced EMF. So either one of those will work. But in our case, we don't have the resistance, so we're going to use the one that uses the current here. Okay. Now, remember the induced EMF for a metal bar moving through a constant magnetic field like this, when the velocity, magnetic field, and length of the bar are all perpendicular to each other, is just the magnitude of V times the magnitude of B times the length of the bar, VBL. So if we plug that in, we'll just have that our power dissipation here is equal to IVBL. So at this point, we can just plug in all of our values, granted that they're in the right units. And it looks like they're all in standard units, so we can just plug them in. And if we do that, we'll get that the power delivered by hand is equal to the power dissipation in our circuit, which is equal to 0.15 watts, or 0.15 joules per second. So there you have it. By using the conservation of energy and our knowledge about motional EMF and circuits, we were able to determine what the power we were delivering to the circuit by hand was.